Hello. Okay, in this video, I want to talk about the work energy theorem, and I'll describe what that is in a little bit after a short derivation. But first, just to remind you of our definition for work. So work is, we'll denote it with this W here, and it's equal to this integral expression. It's a line integral. And the interpretation that we have of this is if I start at some position A, end at some position B, move along the particular path shown, which is arbitrary, could be any path. Then I take every little section of the path, so an infinitesimal section of the path, dl, and then I ask, what's the force there? Looks like this. And then I take the dot product between the force and the little path length. So what that does is it takes the portion of the force that's parallel to the path right there, because the dot product picks out the part of one vector that's parallel to another, and then multiplies those two things together. So it multiplies the parallel component of the force by this little dl. And that's the little bit of work done along this little section of the path. And then I take the integral and I add that up along the entire path. So dl will change, f could change in principle, and I add that up to get the work. What that means intuitively isn't super clear, but the work energy theorem leads us towards a reason for why we have this definition of work. So, okay, so to start here, I want to ask not what is the work done by a single force F, but what's the work done by the net force? So that will look like this. So just replacing the force in there with the net force. So I can do this. I mean, basically all I'm doing is I'm just adding up the forces on an object and then compressing those into a single integral expression. So an integral is a linear operation. So if I added on terms here, like I added another like second force here, something like that from A to B, then I could compress them all into if that was all the forces on an object, I could compress that into the net force here. So all I'm doing is I'm taking the work if I'm looking at the entire net force on an object. Okay, so this is going to be a little derivation to explain why work is important and why we're talking about it. So let me write a couple of things down. First, let me assume that this is a one-dimensional problem. Let's assume a 1D problem here. It'll be, at the end, we can think about how we would generalize to 2 or 3 dimensions. And it's not super difficult, but I want to just simplify and let it be 1D right now. So what that means is, and let's say I'm just talking about an X coordinate. So X is my single coordinate here. So the net force I can write as MA I hat, let's say. So I've only got X direction. And my DL, I can say is DX I hat. Okay, so that's fine. So as an aside here, you can see how we would generalize. So if we wanted to generalize, we would add another term here. We would make this MAX I hat plus MAY J hat. And similarly here, we'd add a DY J hat here. And we can think about how that would work out at the end. Okay, so writing things this way allows us to do some fun things with the integral expression. So the net force will be equal to, starting at A and ending at B. So I'm going to just plug in here. So MA I hat, that's the net force, dotted with DL, DX I hat. So I hat dot I hat gets 1. So if I do this dot product, I guess it's really an X integral. So I'm really integrating from an initial X position to a final X position. And I get MA dx. All right. So here's another thing to remember, that A is equal to dv dt. Okay, and let me plug that in. So the net work is equal to an integral from some initial position to some final position, m dv dt dx. All right, and here's a tricky bit. There's a few ways to think about the operation I'm about to perform here, but I'll just claim, because we're physicists, that we can treat these differential operators as fractions. And we're just going to slide the dt over here onto the dx. So that is, if I imagine I had a numerator that was dv dx and a denominator that was dt, it's a completely valid operation to slide that dt over onto the dx rather than the dv. So that looks like something like this. So m dv dx dt. But now notice, this is just v. This is just the velocity. Dx dt is the velocity. And I really now, instead of an x integral, dx integral, I've got a dv integral. I'm going to have v dv in here. So the bounds of my integration are really an initial velocity to a final velocity. And if I write it like this, m dv times v from initial velocity to final velocity. All right, so this is now something that we can integrate. Let me just write it in a nicer form here. So I'm integrating from some initial velocity to final velocity. M, actually I'm going to pull the m out, aren't I? So the network equals, let me pull the m out because it's constant. And then I've got v dv. Now this is an integral that we can do. We've got v here integrated dv. And that's nice, so let's do it. So we're going to get m times 1/2 v squared, lower bound vi, upper bound vf. So let me write it, let me just expand that all the way out, m, and I'll write it like this, vf squared minus 1/2 m vi squared. All right. This is really cool. Let me do a little work and explain why. So we're going to define some things here. I'm going to define this quantity kinetic energy. So I'm going to define the kinetic energy as 1/2 m v squared. So if I have something with mass and it has some velocity, then its kinetic energy when it has that velocity is equal to 1/2 mv squared. That is a definition. So this is a definition of kinetic energy. And so if you look at our expression for the network here, we have the network is equal to the kinetic energy at the end of our path minus the kinetic energy at the beginning of our path. That's what this means. So we started with some kinetic energy at our initial point, and we ended with some kinetic energy at our final point. And this says that the network is equal to the change in kinetic energy. So if, I guess I could write that out. So this is like the kinetic energy at the end. So kinetic energy final, this is the kinetic energy initial. The difference between them, I'll call the change in kinetic energy, delta KE. So delta KE, delta meaning change. And this thing, this is called the work energy theorem. And arguably, it's the most important result in physics. Later, we'll see this as a statement of conservation of energy a little bit later in a few days. For now, this is extremely useful. All of this, the structure we have for work, the way that it is defined is with this theorem in mind. So this is extremely useful. What this says is, if we know the change in kinetic energy along some path, we know the total work done. We know how much energy was transferred from kinetic energy into other forces. For example, as a problem-solving tool, it's extremely useful, and we'll see some of the ways that it is useful coming up. And this is the work energy theorem. Okay, so I want to give you one more thing to say about it before we do an example. This says that if we're solving problems, when we've been using Newton's laws to solve problems, we had to know about the acceleration of an object at every point from some time to another time. That's how we solved the problems. We knew like what the acceleration was the entire time we were interested in the problem, and then we used that to find velocity and position. This says that we can, if we want to know something about a particle, we only have to know something about the endpoints. Just the change from beginning to end. And that's extremely powerful in a lot of situations. So I want you to keep that in the back of your head. And I want to show you an example now. So let me give me a sec to get that set up. Okay, so here's an example to consider. I guess I'll put a line here so we know it's an example. All right, so we've got a 100-gram ball. It's thrown straight up with some initial velocity, 10 meters per second. How much work is done by gravity as the ball travels to its highest point? Well, we can solve this a lot of different ways. I'm going to solve it with a work energy theorem. One way to solve it that you might consider is just to use the initial velocity and solve for the highest point. So how far it goes up, we know how to do that with kinematics. And then once you know the highest point, you can calculate the work done by gravity by integrating the force of gravity from the initial position to the final position along a path that's straight up, and then calculate the work that way. There's a simpler way with the work energy theorem. So work energy theorem says that the net work is equal to the change in kinetic energy. The change in kinetic energy we know because it is the final velocity is 0, because at the highest point the velocity has got to be 0. So the final kinetic energy is 0. The initial kinetic energy is 1/2 times mv squared. So the mass is 0.1 kilograms. The velocity is 10, so we square that. And if we calculate that out, we get -5 joules. So 10 squared is 100, times 0.1 is 10, divided by 2 is 5. So 0.5 joules is the amount of work done by the net force, which if gravity is the only force here, if we neglect air resistance, that's the net work is equal to the work done by gravity. So really simple, really straightforward. Is a pretty powerful problem-solving technique. What does it mean that this is negative? So there's a lot of different ways to think about this. It's sometimes hard to get a sense for what work represents. So it's good to keep in mind how work is calculated and what the physical situation this corresponds to is. So what's happening is there's a ball that's going up. It has velocity up for this whole problem, but the only force is down, mg. So if we think about how we would calculate work, work is an integral of a dot product. And in the dot product, we're dotting the path length vector with the force. So the path that's being traveled is going up, whereas the force is down. So the dot product we get there is negative. That means that we should expect the work to be negative. Okay, so that's fine mathematically, but that doesn't really provide an intuition about what's happening here. This does, though. So the change in kinetic energy is negative because the velocity started out positive and went to 0. That means that it's slowing down. So if you slow down because the force is acting opposite your direction of motion, then the work is negative. That means that kinetic energy is being taken out of the system by gravity. That's the way we could think about it. And later we'll conceptualize that as, like in a few days, we'll conceptualize that as kinetic energy being traded for gravitational potential energy. So it's not exactly we're losing energy, we're turning kinetic energy into gravitational potential energy. And then if the ball falls back down, we're going to get positive changes in kinetic energy because the ball will start slow and speed up as it falls. That will correspond in positive work being done by gravity. And then we're trading gravitational potential energy for kinetic energy. So work can be positive or negative. It's really important to hang on to the minus sign because that tells you a lot about the physics of what's happening. So I hope that helps as a way to think about why we are using work and the work energy theorem, which we're going to use a lot going forward. And I'll see you soon. Okay, bye.